Welcome back to Differential Calculus. In this video, I want to talk about the mean value theorem. The mean value theorem, alongside the intermediate value theorem and the extreme value theorem, are sometimes collectively called the big three theorems of differential calculus, or of calculus courses in general. They follow a couple of very similar properties, the first two of which are the bane of students everywhere. These three theorems, as you've already seen with the intermediate value theorem and the extreme value theorem, always have very convoluted statements of their definitions, and they are all existence theorems. They tell us that something is going to happen, but they don't give us any tools on how to get to that thing happening. Let me get my head out of the way, and let's start in with that definition here for the mean value theorem. If we let f be a real valued function of one real variable, which is continuous on a closed interval from a to b, and is differentiable on an open interval from a to b. Right. So remember, continuous can be defined for closed intervals by taking the one-sided limit for the endpoints. Differentiable doesn't make sense for a closed interval. Talking about whether a function is differentiable at an endpoint is a little bit nonsense. But for an open interval, we are happy to do it. So the derivative of the function exists everywhere inside of the open interval from a, b. The endpoints might have weird things happening. We don't really care. The function is continuous on the entire closed interval. That's really not a lot to ask. And with just that, we claim that there is a point C inside that open interval such that f prime of C is equal to f of b minus f of a all over b minus a. Okay. Well, take a minute and think about it. F of b minus f of a over b minus a. I'm going to draw a very simplified function here. We have some point A, we have some point B, we have f of a, we have f of b. This function is a lot simpler than it could be, and this still hold, but it's going to be one that allows us to analyze things pretty nicely. All right, so there's the function that we are analyzing. F of b minus f of a over b minus a is the slope. Whoops, let's try again, actually connecting the dots. That's a little bit better. F of b minus f of a over b minus a is the slope of the line that passes through those two endpoints. F prime of C is the slope of the tangent line at some point C. And once again, let's try drawing that a little bit more neatly. That looks a little bit closer. What we're saying is that these two lines have the same slope. They are parallel to each other. All right. And what does that get us? Well, a couple of different things. First of all, I think that looking at this finally gives what are we talking about by the mean value theorem. Even if you have taken no statistics coursework in your previous mathematics career, you should be familiar with the mean as one of several measures of central tendency in statistics. There are a couple of different variants of the mean. There's also the median, the mode, the mid-range, a couple of other things that give you a measure of what is happening to a set of values on average. That's the language we're thinking about here. The secant line, the line through those two endpoints, is the average rate of change of the function on this interval. This is the instantaneous rate of change of the function at this point. So the mean value theorem tells us that at some point in the interval, the value of the function, or the rate of change of the function, is exactly the average rate of change everywhere. If you are looking for an approximation, that's a useful tool, knowing that this is a place where the rate of change is the average, and you can take that as representative of the entire interval, and you can still do some good work with it. That also allows us to make a couple of other very interesting conclusions that are going to pay off for us a little bit later on in the course. All right. Consider a function f of x, which has the property that f prime of x is equal to 0 for every x in some interval. With that, I claim that f of x is a constant function on that interval. All right, and how can we get there? Well, let's think about the mean value theorem. F of b minus f of a over b minus a is equal to f prime of c for some c in AB. We don't know which one. But in this particular case, that doesn't matter. Because we have this property for every c inside of that interval. So it must be the case that f of b minus f of a over b minus a is equal to 0. That tells us, well, assuming that a and b are not the same point, we can multiply by that and get that f of b minus f of a is equal to 0, which is only true if f of b is equal to f of a. All right, that seems to be getting us in the right direction, but it's not quite the entire proof. Right? We now know that the endpoints have the same value, and the function is doing something in the middle. To get the rest of the way, I challenge you to start with f of a, and then pick some other x on the other side. So, for another point, let's say d, in the interval from a to b, notice I have opened it on a, which means that d is not equal to a. Well, then we can make the same argument on the interval from a to d, which means that f of d is equal to f of a. And we can do this for any point in that interval. So for any x in the interval from a to b, f of a is equal to f of x. And that's what it means for a function to be constant. So if we have a function whose derivative is 0, we know that the function is constant. We already knew that in the other direction. We knew that if we had a constant function, the derivative would be 0. But that's not the same thing. This is a huge step for us that we're going to build off of in a couple of weeks. Not immediately, but we'll get there. We're looking to try to figure out, when is the derivative invertible? When is there some inverse derivative function? And it turns out that that doesn't quite exist, but there's a lot that we can go on that will get us towards there, that we'll be building up for a while. But it relies on this logic. It relies on this idea that not only the derivative of a constant is 0, but when the derivative is 0, it had to have been the derivative of a constant. That fact is going to make our lives so much easier a little bit further down the road. Right, here is another situation. The logic is going to be somewhat similar to what we just did, but a little bit easier. Let f be a real-valued function of one real variable, which is continuous on the closed interval from a to b, differentiable on the open interval from a to b, and f of a equals f of b. I want you to prove that f has at least one critical value on the open interval from a to b. All right. Asking you to prove something is not my usual in this course, but this lesson very much is rooted in logic and not in computation, so I don't have a lot of other recourse. With that in mind, I do want to give you a couple of nudges in the right direction. Notice in the statement here, we have a real-valued function of one real variable, it is continuous, and it is differentiable. Those are the requirements for the mean value theorem. So the mean value theorem should help you in this. The other thing I want to notice here is that we are trying to show that the function has at least one critical value. We're not trying to find the critical value, we're just trying to say that it exists. Right? The mean value theorem, the intermediate value theorem, those are really good at saying that something happens without telling you when or how it happens. Right? So there's some starting point. We're definitely going to use the mean value theorem here. Other thing is, thinking back to what we did in a couple of earlier lessons, what is a critical value? What are we looking for in a critical value? And how can the mean value theorem help you get there? All right, with those things in mind, see what you can do with this one, and I'll see you in the next video.